Welcome to the first stats video for the year. The topic for this is two-way tables for categorical data, or in other words, contingency tables. What I want you to remember about a video is that the beauty of it is if I go too fast or you need to write something down, you could always pause, rewind, replay to make your learning experience better. Okay, so let's get to it. This is basically the bulk of Chapter 3. Now, with categorical data, there's not a lot we can do with it. For example, we can't take a blue-eyed person and a brown-eyed person and average their eye color and get something meaningful. The only thing we can do is count them and turn them into proportions and then specific types of graphs, like pie graphs and bar graphs. So looking here, this is a two-way table. It has two variables. The first variable is, do you buy recycled filters? And by filters, they mean coffee filters. And the other variable is quality. What do you think of the quality of recycled filters? Do you think they're higher, the same, or lower? So in terms of vocabulary, when we talk about a distribution, what we're saying is, what values can a certain variable take on? And then how many of each of these values can it take on? So for example here, we have a distribution of whether they said yes or no to the filters. Do you buy them? The values are obviously yes and no, and then we can count them. And we can see that 36 people said, yes, I buy them, and 97 people said, no, I don't. If you look at this, you can see that these values that I just gave you are in the margin of the contingency table. What this basically means, sorry about this, I'm just trying to turn this around on my little screen here. There we go, is that the totals are 36 and 97. This is a marginal distribution because we can find these values in the margin. Now, for recycling status then, I could say, if I'd like, there are 36 yeses and 97 nos. This isn't as meaningful as having them in percents. So what I usually do is divide by the total, and that would now give me that 27% said, hey, yeah, I recycle. And 73% said, nope, I don't recycle. So this would be the marginal distribution of recycling status. Again, we found it in the margin. But I could have said, what's the marginal distribution for quality? If that were the case, I would have to be looking at the other margin and say, well, what proportion, say higher, same, or lower? Just like before, I could put in the numbers here. I could say like 49 said higher, and 32 said they're the same, and 52 said, they're lower. But really what I'd much rather do is have these as percents because they're more meaningful to people. So I would say 37%, actually I'm going to take that little decimal away and just write it as 37% said higher, and 24% said the same, and 39% said lower. And I'm getting these values just by taking the total for higher and dividing it by the 133, or the same total and dividing it by the total. Now, these are just simple calculations to get a marginal distribution. And the key is you find marginal distributions in the margin. Okay, next up is what we call a conditional distribution. It's basically a distribution of a variable when we restrict the who. Now, you've all had restrictions before. Your mom and dad say, hey, you can't go to the movies unless you do your homework. They're putting a restriction on you. Well, that's exactly what a conditional distribution does. It puts a restriction on you. When I say, what is the conditional distribution of quality for each recycling status, I'm saying I'm limiting the who to the recycling status. And there were two recycling statuses. They were yes and no. And so what I'm basically saying to you is, if they said yes, what proportion of people would say the quality is higher, the same, or lower? If they said no, what proportion said higher, the same, or lower? So a conditional distribution is no longer the totals from the margin. It's limiting yourself to some particular column or row. So for example here, if I had said, like I said, the conditional distribution of quality for the recycling status of yes, well, now I'm limiting myself to these 36 people. And I'm saying out of those 36, what percent thought higher? And in this case, 20 out of 36 is 56%. 7 out of 36 is 19%. And 9 out of 36 is 25%. And you can see pretty clearly that if they thought that if they recycle, they really thought the quality was higher. Now, if we go to the no column and restrict ourselves to the no's, now we're saying to ourselves, well, of the no's, which there are now 97 of them, what percentage thought the quality of the coffee filters was higher? That's going to be 29 out of the 97, which turns out to be 30%. 25 out of the 97 turns out to be 26%, and 43 out of the 97 turns out to be 44%. So I want you to notice the condition that I just did isolated the columns. And if we go look at each of these, we can see that they add up, each of these distributions, conditional distributions, to 100%. Okay, now I could have easily have reworded the question, which is why I bring you down here. And I'm just going to point here and say to you, what is the conditional distribution of recycling status for each quality type? Now you notice I'm specifying quality type. So now, when we look at this, there are 3 quality types. Oh, I'm moving the wrong thing. There we go. Higher, same, and lower. So now, instead of going down, I'd say of the higher, what percentage recycled? And I would see it's 20 out of 49. And if I go to my handy dandy calculator onto the scratch pad, 20 out of 49 is about 41%, which means that the yes would be 41%, which means if I went across, the no would be 41. What would we have to add to that to get to 100? You tell me. So we could have gone and done our distributions sideways. Okay. With this said, one of the pictures that I love to make is a segmented bar graph. This is the best kind of bar graph when you're comparing two variables. What I want you to notice is I've done this for the conditional distribution we did of yes versus no's. So I have 1 bar for yes, 1 bar for no. Notice that the bars go up to 100%. And also notice that I've labeled the axes. Do you recycle? This is percent, and I have a key. And to simply make this graph, I can use the table that I've just made. For example, if you go back, you could see the yeses had 56% recycled. That's the height of this bar, 56%. And then if we go back, to the same, that's 19%. So I added 19% higher to bring me to the top of this bar. And then whatever left had to be the lower. So each of these percents corresponds to the percent on here and adds to 100%. Looking at this, you can see a really clear picture. If I tell you someone recycles, what would you say they think about the quality of the filter compared to someone who doesn't recycle? Yeah, there's an association here. And that association is that if you recycle, you are more likely to think the quality is higher. Here's a similar graph for completely different data. It looks at the variable area of residence, which has 3 values, rural, suburban, and urban. And it looks at political party. And you can see the key for political party here. And this is a beautiful graph. Notice it has a title. Every axis is labeled. I can see the values of the variable, and I have a key. When you have a quiz on this, this is what I want to see in a graph. Okay, when you look at this graph and I say to you, does area of residence tell you anything new about their political party? Can you tell me anything? Can you tell me, well, if they're rural, they're more likely to be this? Or if they're suburban, they're less likely to be this? No. The area of residence tells you nothing new about the political party. This means that the two events are independent. In fact, what do you think the contingency table would look like if we went back and we made one of these contingency tables for these two variables, political party versus area of residence? What do you think would be true of every column? Well, this leads to our definition of independence. Two events are independent if the conditional distribution of one variable is the same for each category of the other. So if you go back to this picture, you can see that for each category of political party, rural, suburban, and urban have the same percentage. They have the same percentage of Republicans, they have the same percentage of Democrats, roughly the same independents, and roughly the same others. So, kind of summing this up, two-way tables are a great way to look at categorical data of two variables. We have two types of distributions that we look at. The first is the marginal distribution. These are the totals, which can be found in the margins, just like the margins of your paper. They tell you how many of each of the variables on the margin there are, but we like to turn these to percents. Conditional distributions limit the who. They tell you, well, if they're recycling, yes versus no, what do we think the distribution of quality would look like? Or we could go the other way. If we say, for each type of quality, what are the percentage of yeses and nos? So the key here is reading really carefully to see which variable you are making the condition. For example, here it was for each recycling status, which was yes and no. And then we looked at this idea of independence. Two variables are independent, basically, if you learn nothing new. And when we look at this segmented bar graph, we look at it and we say, wow, I did learn something new. If someone recycles, they're more likely to say the quality is higher. Versus this segmented bar graph that says, gee, where you live really doesn't tell me much about political party, which led to our definition of independence. Have fun trying the next worksheet as your guide as you go along.